Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to go over synthetic strategies of carbonyls, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
So to summarize all of the aldehyde and ketone reactions that we have learned so far, here is an interconversion map of functional groups starting with either a ketone or aldehyde. Hydrate formation with H3O plus in water could occur to form a hydrate or geminal-diol. Acetyl formation with H2SO4 and an alcohol could occur to form first a hemiacetal and then an acetyl group. Baeyer-Villiger oxidation of a ketone or aldehyde could occur with a peroxy acid like RCO3H to form an ester or carboxylic acid. Cyclic acetyl formation could occur to protect an aldehyde or ketone using H2SO4 and ethylene glycol. A cyclic thioacetal could be formed using dithiol and H2SO4. An imine can be formed with H2SO4 and a primary amine, or an enamine can be formed with H2SO4 and a secondary amine. Now, if the R group in a primary amine is replaced with a hydroxyl group, then an oxime could be formed. Or hydrazine could be used as a nucleophile to form a hydrazone. Both oximes and hydrazones have the same mechanism as imine formation. Now going on to hydrogen and carbon nucleophiles that could attack aldehydes or ketones, the carbonyl could be reduced using lithium aluminum hydride in the first step and water in the second step. Or sodium borohydride with an alcohol could be used. If there is an increase in carbon count, an organometallic reagent like Grignard or organolithium could be used. To add a cyano group, you could use HCN and KCN to add a nitrile group. And lastly, Wittig reactions can be performed to change a ketone or aldehyde into an alkene. So when you're doing a synthesis problem, you want to consider two particular changes when comparing the reactant to the product. First, take note of any carbon count changes, and then think about what particular reactions may have caused such a change. For instance, reactions that increase carbon count when going from reactant to product are Williamson ether synthesis, alkylation with a terminal alkyne, an organometallic reaction, alkoxymercuration demercuration, a ring opening of an epoxide, Friedel-Crafts alkylation or acylation, or any nucleophilic addition to aldehydes or ketones using the following nucleophiles. Furthermore, reactions that decrease carbon count include ozonolysis of a linear alkene and acidic cleavage of an ether. And another change to take note of are any functional group changes, and you can use the reaction maps as a guide for interconversion between different functional groups. Now let's take a look at a synthesis problem. Propose an efficient synthesis for the following transformation. Before even beginning, let's first count the number of carbons in the reactant and product. Notice that the reactant has 8 carbons and the product has 10 carbons, so we should think about what reactions we currently know of that increase carbon count. So let's start with possible route number 1. One reaction that comes to mind that increases carbon count is an organometallic reaction. Now, since a Grignard reagent won't attack an alkene, we have to convert the alkene into a carbonyl, which may take a couple steps. So take note of the specific carbon that the new carbons are being added to in the product. One way to form a carbonyl from an alkene is to first add an alcohol group in this case to the less substituted position of the alkene, and then oxidize the primary alcohol using PCC, DMP, or SWERN. Then we can use this aldehyde to perform a Grignard. To increase carbon count by 2, we can use ethyl magnesium bromide as our Grignard reagent to get the following alcohol. Then in the last step, to form the alkene, we can perform an E1 reaction using H2SO4 that follows Zaitsev's rule to specifically deprotonate a beta hydrogen from the beta carbon with less H's to finally form our product. But now let's think about a possible second route. Is there a more efficient, aka shorter route that can get us to our product? Well, we could do ozonolysis to cleave the alkene, which is a direct way to form 2 carbonyls. Then we can perform a Wittig reaction with just one of the carbonyl groups to install an ethyl group, which occurs in one step. So although both pathways are correct and acceptable, the second route is much more efficient because it requires only 2 steps. So the final proposed synthesis starts with ozonolysis, followed by a Wittig reaction to afford the final product.
Organic.